In this work, we present an atmospheric model tailored for the interactive visualization of planetary surfaces. Our model provides a complete framework for the absorption of light by small and large particles, such as the oxygen and ozone molecules and Mars dust particles. We demonstrate our results using Earth and Mars as examples.
Nowadays, technology is developed for a single audience, assuming that one size fits all. Nevertheless, we all have individual differences, such as personality. Taking into account how personality affects preferences, we study whether it has an effect on hierarchy, evolution over time, and comparison context regarding information visualization. We leverage all personality variables from the 5-factor model and the locus of control with correlation and clustering approaches, showing promising results.
This study presents a method to explore hierarchical data by improving RODVIS, one of the visualization techniques for multidimensional data. The user can set options for nodes and check the data in groups or individually in the RODVIS. 3 subviews at the right enable the hierarchical clustering structures of selected data and allow the user to grasp the features of selected data. As a result, this system allows more detailed insight into the data while solving the node overlapping problem.
Existing visualization tools for deep learning classification are mostly working on natural images with mutually exclusive classes. The classification of X-ray scattering images is more challenging since their multiple structural attributes have complex relationships. So, we built an effective visualization system to study the model performance and to find questionable labels or outlier images for scientists' further improvement.
Designed in response to the COVID-19 pandemic, the novel visualization technique we are calling GOWNS accommodates continuously incoming and increasing case data without distorting past data. Layering linear scale graphs shows both small and large numbers. This allows more detail to be seen when scrubbing through time and comparing regions by realigning the GOWNS based on case numbers.
Data GIFs are enjoying increasing popularity on social media as a format for data-driven storytelling with visualization. Simple visual messages are embedded in the short animations and are played in automatic repetition. Here we present a structured design space and a set of design instructions to create effective data GIFs.
We propose V2V, a comprehensive pipeline for variable selection and translation for multivariate time-varying data. Our approach contains feature learning, translation graph construction, and variable selection. To demonstrate the effectiveness of our approach, we compare histogram matching, pixel to pixel, and cycloGAN to evaluate variable translation. In addition, we also compare an information-aware framework to evaluate variable selection.
What is insight? It is a question that has bothered visualization researchers for a long time. We're wondering whether visualization practitioners think about data insights in the same way as visualization researchers do. So we interviewed 23 visualization practitioners to understand how they think. To find out more about what we found,
All right. So hello and welcome everyone to the session Making Sense of Text. My name is Florian Heimrl, and I'm the chair for this session, in which we have 6 exciting talks. And the way that this will work is that after each of the talks, which are pre-recorded, the presenter will be available for a live Q&A segment. So if you have any questions about the work, write them into the chat, either on Discord or YouTube, and I'll be watching those and take note of the questions and then ask them directly to the speaker on the stream. All right, with that, I think we can get started right away. Our first speaker is going to be Robert Laramee, and he's going to talk about TransVis, integrated distant and close reading of Othello translations.
TransVis, integrated distant and close reading of Othello translations. TransVis is a design study that we propose to integrate close and distant reading of multiple translations. It's an interactive tool that is designed with close collaboration with a domain expert in translation studies to deliver a novel design that is capable of exploring and analyzing the interrelationships between translations. The design is guided by the visual information seeking mantra to provide an overview first, zoom in into the segments level, and then provide details on demand. 5 tasks that are identified based on the typology of visualization tasks by Bremer and Monsner in order to action 6 requirements. TransVis contributes the following: a novel visual design that supports comparison of multiple parallel translations, customized mechanisms for rapid and interactive filtering and selection of a large number of German translations of Shakespeare, interactive and dynamic analysis of similarity metrics to support comparisons and analysis of customized parallel translations, examples, detailed observations, a case study, and domain expert feedback from a specialist in German translations of Shakespeare. We divide the previous work into mainly 3 groups. Visual comparison of general text, which includes designs that support the analysis and visualization of a single or more unrelated texts. Visual comparison of parallel texts, which includes designs that support the analysis and visualization of related texts, such as editions or translations. Previous work on Shakespeare's Othello, which includes designs that analyze and visualize Othello German translations. We summarize the previous work that study related texts in Table 1 in the paper. A group from the arts and the humanities working on a project called Translation Arrays, Version Variation Visualization collected 55 translations of Shakespeare's play Othello. The translations span 1766 until 2010. So far, 38 translations of the collection were optically scanned from paper prints, corrected from OCR errors, segmented and aligned with the English-based text to create a parallel corpus. The translations were collected over a time span of 2 to 3 years from various sources, such as libraries, second-hand booksellers, archives, theater publishers, and theater companies. The translation data is stored in XML format on the project's website. The Edmv Metrics was introduced by Cheesman et al. To quantify how a given base segment is interpreted and translated between parallel texts. ED characterizes the translated segments in terms of distinctiveness. A higher ED value indicates higher dissimilarities from other translations. VIV, on the other hand, is the average pairwise distance between every two segments projected on the base segment. VIV represents the stability of the base segment. A high VIV value indicates low stability, which means the segment's translations vary considerably between authors. Along with the domain expert, we established and incrementally refined a list of requirements. An application that enables comparison of translated parallel text, a visual design that supports both close and distant reading, a layout that supports close reading for further detailed analysis, a visual design that considers stable versus unstable translations, interaction that enables customization of the translated text, interaction that supports general exploration and analysis. Based on the requirements and the typology of visualization tasks, we established these 5 tasks. In the discovery process, the user should be enabled to explore the alignment overview in order to identify a region of interest. After identifying a region of interest, the user may navigate the space leveraging smooth zooming and panning. As the user navigates, multiple levels of details are aggregated and rendered. As the user performs task 1 and/or task 2, the user may apply different filtering and selection tasks to assess the exploration task. As the user performs task 2, the user may select a segment to obtain details on demand. As the user performs task 1, task 2, and/or task 4, the user may perform interactive comparisons of the parallel translations, exploiting metadata based on the alignment of speeches and text similarity metrics. Our design is composed of 4 main components that aligns with the visualization information seeking mantra: an alignment overview, an option panel that provides interaction and exploration means to the alignment overview, the detailed view, and the term level comparisons view, TLC. The alignment overview presents a parallel view of translations, and in each translation it presents the encapsulated structure. It provides distant reading and a general context for understanding the collection and conveys the whole dataset in one visual layout. The alignment overview leverages interactive capabilities to enable the user to explore and find interesting patterns and features within the collection. It enables users to examine significant larger patterns in the translations which are not readily viewable from a narrow or detailed view. Each parallel line shows a translation, and each rectangle represents a segment. We incorporate Edmv analysis to detect variation among translations. Each segment within an alignment path is assigned an ED value, and each path is assigned a VIV value, which is projected on the English segment. The user can drag and drop a translation to change the order of translations. When zooming, the user can reveal the text and obtain close reading of the collection. The Options panel incorporates exploration and interaction means to customize, change, or edit the alignment of a view. It facilitates an interactive searching mechanism. From the Options panel, the color schemes can be changed. Also, the mapping can be changed to segment length, speech length, or to Edmv values. The user can change the order of the translations based on different sorting options. The user can enable or disable the option of interactively aligning the translation vertically when selecting a segment. The user can filter the collection to show specific speaker segments. Also can add or remove stage direction segments. From the time-oriented thumbnail view, the user can customize the collection by adding and removing translations. The third main component is the detailed view, which is the focus subset that the user is interested in after performing filtering and selections in the alignment of a view. The detailed view shows a close reading of the user selected speech along with the aligned translations. It stores both the aligned segments and the alignment overview state, so the user is able to revisit any previously selected paths for further analysis. Also, the text in this view is accessible to the user and can be copied to be used beyond the tool. The Tlc View visualizes all of the vocabulary used in Edmv. Each parallel line depicts a translation, and each polyline represents a word. The word value for each translation indicates the term weighting that contributed to eddy analysis. The Tlc View incorporates a word list accompanying the timeline graph. The user selects an interesting alignment path and drag and drop to generate the Tlc View. The user can choose a word from the list and the corresponding polyline will be highlighted. Also, the user can select polylines from the timeline and the corresponding words will be highlighted. The design was evaluated through domain expert feedback sessions. We conducted 9 in-person sessions over 5 months. All of the sessions are video recorded for post-analysis. TransVis is also evaluated using case studies to address 2 questions. Do apparently identical texts differ? Discovering the work of editors and rewriters. Do translators differ? The individual distinctiveness of translators. We see an example of translation variation between 5 editions of Bautzen, 1832. On the left, Wolf's translation stands out due to the high values of eddy. After deselecting the Wolf's translation on the right, we can see more variation among the 4 remaining translations. The domain expert states, this reveals that the 1926 so-called edition, revised by Max Wolf, is not really an edition of the Bautzen translation at all. It's almost a completely new translation created by editing Bautzen. For the emerged variation after the deselection of Max Wolf's translation, the domain expert states, some of this variation is due to historical spelling changes. Some changes are more significant. They are caused by editors aiming to improve the Bautzen text they have received, making it easier for readers, actors, and audiences. The domain expert explores variation between these translations at the term level using the Tlc View, with the segment starting with the AIM reports. The domain expert states, the segment was translated by Bautzen as conjecture reports, 1851. This is a very compressed expression, meaning people making conjectures report. Not easy to follow and also difficult to speak. Some later editors changed this to estimating people report, 1923. Supposition reports, 1947. Rumors report, 2000. The Tlc View shows this clearly when examining the summits of the translation's dimensions. During the domain expert feedback sessions, different observations were discovered. For example, in a speech Iago says, if thou dost, I shall never love thee after. All other Bautzen translations use the word Freundschaft, which means friendship, except the 1926 edition uses the word Liebe, which means love. The domain expert justifies, again, intensifying and bringing back the hint of homoeroticism in the original, which the classic text censored.
Yes.
Another example that was discovered during the feedback session by a non-German speaker and then justified by the domain expert, that there are 3 translations that stand out from the rest. The 3 translations have 3 recognizable words with high values which can be easily noticed in the Tlc view. These words are different translations of the English word moor in the context I hate the moor. The domain expert validates the discovery and reasons that the word is translated in different ways in different times with different political implications. More examples of use cases and observations can be found in the paper. A full demonstration of TransVis features can be found on the DataVis Bob YouTube channel. Future work. We are looking forward to applying TransVis to other translation corpora. Incorporate semantic clustering and structural similarity between translations. The rendering could be updated to reflect this when zooming in or out of the scene. Scalability is a challenging issue when dealing with large parallel text, and more in-depth research to address this is encouraged. Thanks for watching.
All right, thank you. That is really interesting work. So there is one question from the chat. Did you think about combining your system with a semi-automatic or automatic approach for the alignment detection to adapt it to other text corpora? And what will be the challenge to do this?
Yes, thank you for that question, by the way. We definitely have thought about that. And in fact, we have published a paper on that topic actually already. The paper is called AlignVis. Actually, I can't remember the subtitle of the paper, but you can find it in the IV conference proceedings for 2020 and a copy of it on my webpage that talks about semi-automatic alignment and a visual interface for semi-automatic alignment. Yes, and the second part of the question was about applying it to other languages, is that correct?
To other text corpora, yes, and what the challenges would be.
So this is a very special case. It's the case of parallel translations. So as long as the text is parallel translations, it should theoretically be quite straightforward to adapt it to those other parallel translations. All the parallel translations would go through the same process, the same processing pipeline.
All right, thank you very much. There is another question. Could you use your system to help isolate and compare the unique languages, the unique language associated with each translation?
Yes, so that is definitely one of the goals of the work. One of the goals of the work is to identify unique language, and we do this with using both statistical metrics and visual metrics. So 2 of the statistical metrics we talk about are the eddy value and the viv value, and these are statistical measurements that quantify the deviance in translation. So if an author has a special kind of deviance in his word choice, that will be highlighted by the statistical measures. And in terms of the visual interface, we can map color to those deviance values. So any translations or any word choices that are very unusual can be highlighted by color, for example. There's also a special view dedicated to picking out outliers in the language, and that's something we call the TLC view. So it's a series of parallel line charts. And the unusual language sticks out as outliers in that view, in that detailed view.
Mm-hmm. All right. Well, thanks a lot, Robert.
Thank you.
And our next presenter is going to be Dora Kiesel, and she is going to talk about the topic of visual analysis of argumentation in essays.
Hello everyone, my name is Dora Kiesel. I am with the Virtual Reality and Visualization Research Group at Bauhaus Universität Weimar and going to talk about the visual analysis of argumentation in essays. Analyzing argumentation is subject to various fields of research, including computer linguistics or digital humanities, and still involves reading large amounts of texts, analyzing tables of abstract numbers and their statistics, and staring at argument maps, for example these here from Argunet or Rationale. The typical tasks, like finding common structural and temporal patterns, comparing the structures of sets of text, or finding texts containing specific or uncommon structures, are almost infeasible using current tools. To improve the situation, we developed the argulines. Each arguline represents a single essay. The red, green, or blue glyphs each represent an argumentative text chunk, or argument unit. Blue is the thesis statement or major claim, green units support the major claim, and red units contain counter-arguments. The argulines are constructed from an essay by first figuring out the thesis statement or major claim of the text, then marking the statements or claims made in favor or against the major claim in green and red respectively, and finally find the premises related to the found claims. These marked argument units are then abstracted from the text to rectangular glyphs and transposed to match the usual orientation of an argument map, figuring text progression from left to right and the argument depth from top to bottom. To let the major claim, the unit that defines the stance and the topic of the essay, pop out among the other units, its rectangle was tilted to a diamond. Finally, the argument tree is compressed to form one line, compressing the height of the glyphs depending on the original depth level to incorporate depth information. Using the argulines, one can compare the structural properties of these 14 essays from the argument annotated essays 2 corpus without the need to read them. The first claim or rectangle is read in all cases, so they begin with arguments against their major claim. 9 of the essays start with a major claim shown as blue diamond in the introduction, and restate the major claim a second time later on as part of the conclusion. As you can see here, our system figures the argulines as overview and detail. The overview on the right-hand side figures miniature versions of the argulines to show the whole corpus. The detail is for closer inspection and interaction. The corpus is ordered by the position of the con argument units, shown as red symbols. First those beginning with con units, then those with con in the middle, those ending with con units, and finally those that do not incorporate any con units at all. These different positioning of pro and con units translate into different argument strategies that aim at convincing the reader to follow the major claim of the essay. Look at this! There is even a single text that has only con units. How can that happen? Let's have a look. The text actually does contain some typical discussion markers, like on the one hand and on the other hand. It seems to be just an error in annotation. Let's go back to the overview. Since different conclusions can be drawn from different orderings, it can be changed according to the user's need. The current implementation supports 8 different sorting orders that have been suggested by our experts. The most important of which are the positioning of pro and con units, the ratio of pro and con units, and the number of units overall. Looking at the overview visualization, one gets the impression that shorter texts tend to contain more con units than long texts. This hypothesis can now easily be proven by selecting the shortest and longest texts and reorder the list to ratio of pro to con. And indeed, the purple segments show the shortest texts are seen on top, where the highest con rates are, while the markings for the orange selections with the longest texts start notably further down.
For analyzing and comparing larger sets of essays, we developed the argument unit occurrence tree. A single essay is represented as a tree, showing its argument units as rectangular bars. As before, the major claim is colored blue and forms the root of the tree. The points or claims in favor or against the major claim are drawn below and spanned by a gray line to show their relation. The small stub between the last two claims marks the position of the major claim within the text. In our example, the first claim has two premises supporting the parent claim, and the second claim has one that supports its parent in attacking the major claim. If we now add the argument unit occurrence tree of another essay, both trees are merged to show all units of both trees. The bars of the tree become histograms to show the probability of the argument unit to occur in the merged set. So the histogram bar of the first claim is fully filled, showing that both trees have this unit. But it is half green and half red, showing that half of the merged essays have a first claim that attacks the major claim, and the other half has a unit there that supports the major claim. Adding another essay, this time one that states the major claim 2 times and has only 3 claims, results in a tree with 2 major claim representatives, where the second one is filled to only 1/3 and a fourth claim that is filled to only 2/3. Now we are able to interpret and compare the 2 argument unit occurrence trees that each represent 21 essays. Both sets have only 1 major claim and between 2 and 4 claims. The main difference lies in the distribution of pro and con units. The upper set begins with arguments against the major claim, while the lower set has higher probabilities for con arguments in the later parts of the essays, suggesting that they end with a con argument. Both visualizations in the text view are sensitive to visual linking and filtering to facilitate finding relevant texts. Additionally, the visual links augment each view by providing extra information. Hovering, for example, over a merged unit in the argument unit occurrence tree highlights all contained units in the argulines, thus providing information about their position in the texts. The visual filter follows the linking concept. If an argument unit is clicked in any visualization, the list of essays is filtered to essays that contain that unit. So the nodes of the argument unit occurrence tree can be used to filter by position or path in the argument tree, where the argulines are used to filter by position in the text. In the sequence, we filter 2 identical sets of text, such that the first claim of the upper set only contains pro units, and the first claim of the lower set only contains con units. This way, we are able to find out structural differences between sets of text with different argumentation strategies. Here, for example, we can see that the argument of the first claim in the upper set is much more elaborate, both broader and deeper, than the first claim in the lower set. This is because the most important and therefore the most elaborate argument in the essay is usually the first in favor of the major claim. The system has been developed in a user-centered manner, in collaboration with 2 colleagues at our institution who are experts in the fields of computational linguistics and text retrieval. To this end, we regularly conducted interviews in which new ideas were discussed and new features tested. Early prototypes tried to incorporate argumentary and positional information into one visualization, and rewarded this effort with clutter and overplotting. Once freed from the idea of having to have everything in one VIS, the argulines could evolve and were received enthusiastically. While they could solve a lot of problems of earlier efforts, still our experts found the necessity for an aggregated view and visual filter facilities that would help them in their usual tasks, like finding common patterns in sets of texts
or to find texts with specific structural properties. After we had developed them to our satisfaction, we conducted a final review with 3 external experts. The linguist and computational linguist found the argument unit occurrence trees particularly useful, since comparing large sets of essays with each other is otherwise laborious. The argulines were the visualization that was received most positively, because they are so easy to understand and use. One expert stated, "You can see very well how different people argue. Some keep themselves short, try to be succinct, and yet illuminate both sides. Others like to hear themselves talk and write endlessly about their own point of view." With our experts, we found some odd structures in the argument annotated essays 2 corpus. There are 18 essays that repeat the major claim 3 times. It seems odd why one would repeat a statement 3 times in such a short text. So let's have a look at an example. It actually does not repeat the statement of the original major claim, but extends it. The phrase could also be seen as a claim supporting the major claim. Let us have a look at the original annotations for this essay. The essays of the corpus have been annotated by 3 independent annotators in a 2-step process that is depicted in the annotation view of the argulines. It extends the original line to encode the relative positions and lengths of each argument unit within the text and adds 1 line for each annotator in each of the 2 annotation phases. In the first step, the text annotation step, the position, lengths, and types of all units are annotated. In the second step, the association step, relations between the premises and claims are added to the consensus of the first step. So if the annotators had different opinions regarding the type of the argument unit, we will find differences in the annotators' argulines in the text annotation step. And indeed, all annotators had different opinions regarding this unit. To summarize, we have developed and evaluated an interactive visual analytics system for computational linguists and digital humanists that allows the analysis of argumentation in essays far beyond the usual texts, tables, and argument maps. To allow a deeper analysis of the semantics within the argumentation, we plan to extend the system to not only show stance, but also the semantic role of an argument unit, whether it is a conclusion, restatement, counter-argument, for example. Encoding established schemes, like arguments from examples, expert opinion, or evidence, as glyphs, to summarize large argument structures, or to examine them from a different perspective is also an exciting challenge. For a quicker assessment of the diverging opinions of annotators during the annotation, or the confidence level of an automatic structure classifier, the argulines could be extended to show uncertainty information, for example by distorting, blurring, or morphing the glyphs. We believe that these enhancements further increase the versatility of our system for visual argumentation analysis in essay corpora. Thank you for your attention.
Oh, sorry about that. All right, thank you very much, Dora. This is very exciting work. There were a range of questions from the chat. One of them was, there was a question about how the claims were extracted from the text. Was that done manually, or is there a way, or have there been attempts to automate this?
They have been created manually, yes, with 3 people annotating each text and then extracting or using that, the annotation that suited most of them. The corpus actually has not been created by us, but by a team at the University of Darmstadt. And it actually was created as a ground truth corpus for training classifiers to do this automatically, but that did not work very well as of yet. So the work is not good enough for actually to actually be usable yet. So we have to do it manually now. But I hope it will be in the future that we don't need to do this manually.
All right. Okay. Have you thought about how to scale up the encoding scheme to more than 2 categories?
Well, there are multiple ways to do this. And yes, we have thought about it because we were thinking about not only encoding pro and con, but also different types of well, premise types, so to speak. So there are possible facts or examples or something. And we there were many ways that we could do this. We thought about, well, just expanding the color scheme so that we do not have only red and green, but let's say 5 or 6 different colors, which would be the simple way. Or to use different symbols would be another way, which would break a bit with the argument occurrence tree, but would work as well.
All right, okay. Well, thank you very much. There is a couple of additional questions. I will post them into the chat. And if maybe you can answer them there.
I will do.
All right.
Thank you.
Well, thanks a lot. And our next speaker is going to be Tariq Yousef. And he is going to give us a survey of text alignment visualization.
Hi. I am Tariq Yousef from Leipzig University. Today I will present our paper, A Survey of Text Alignment Visualization. It's a joint work with my supervisor, Professor Stefan Jänicke. Alignment refers to the discovery of similar and different patterns among 2 or more data objects. It's a fundamental and widely used technique in many fields like NLP, computational linguistics, and digital humanities. In this survey, we discussed 3 scenarios. The first scenario refers to the collation task in textual criticism, aiming to investigate textual variation across different versions of text and create critical editions. The second scenario is concerned with the discovery and analysis of reused text passages within a collection of text. The third scenario is translation alignment, which is a fundamental task in machine translation system, where text fragments are aligned with their translations at word, sentence, or paragraph level. With the given survey scope, we search for related tools and publications. As we ourselves are active researchers in this area, we already had a proper body of related works to start with at hand. We additionally consulted the TextVis browser to extend our collection. We further used Google Scholar to browse visualization and digital humanities and computational linguistics journals and proceedings using related keywords like alignment visualizations or collation visualization. In addition, we used the standard Google search to find related translation tools that apply visualization means. The final collection of our survey is listed in this table. We reviewed 40 visual interfaces that support text alignment analysis and classified them in 7 state-of-the-art visualization approaches. We start with sequence-aligned heat maps. They serve as a summarized overview of alignment patterns among different source text, and they are typically used to navigate to text units of interest. Each row represents a text from the corpus, which is visualized as a sequence of colored rectangles. Rectangle stands for a text unit, which could be sentence, paragraph, or chapter. Text units are ordered as they appear in the text, and the aligned tokens are placed on the same vertical axis. In this screenshot, we can see the Lyra framework. It applies a coloring schema to indicate different degrees of variation. The lighter the color, the more similar the corresponding segments is to the other parallel segments. The second model is grid-based heat maps. They illustrate alignment patterns among two texts of a corpus. Each cell of the grid represents a juxtaposition of two text units. Typically, color is used to inform on particular feature of the relationship between the two units, such as alignment types or matching scores. Here in this example, we can see the text reuse grid, which provides alignment information for an entire document collection. Here we see the ASV people American Standard Version. A cell here stands for a pair of processed documents, and the color informs on the frequency and type of occurring text reuse patterns. Aligned barcodes, they often appear as overview visualization in addition to side-by-side views. They direct the user to interesting patterns of consecutive alignment units or transposed passages. They are limited, as we can see, to two text variants on line or sentence or paragraph level. This makes patterns of subsequent aligned text fragments as well as transpositions easy to spot, as we can see. Text-oriented heat maps focus on a singular text overlaid with aligned information. Typically, words or phrases receive a colored background indicating how often they appear in the other text of the corpus or how strongly they vary. Here in this example, we see the juxtacommons uses this technique to illustrate textual variation among multiple witnesses. It utilizes different degrees of saturation to display different levels of variance. Here we can see from the base witnesses. Side-by-side view visualizations are the most commonly used technique to visualize aligned text at different levels. It locates the compared text alongside each other, and aligned units are highlighted. Usually a navigation bar or aligned barcodes are usually associated with the side-by-side model to facilitate the navigation through the aligned units in case of long text. Here we can see a translation alignment between three texts in three different languages using Ugarit aligner, and here the versioning machine view in juxtacommons. The major constraint of side-by-side views is the limited screen width, which makes them applicable for a limited number of text variants. Also, users might also get distracted since they have to move the eyes between parallel text to identify positions of variance. Tabular views visualize word-level variations for small text fragments, such as sentences or short paragraphs. It's represented in the form of a table. The rows represent different aligned sentences. Columns stand for aligned tokens. Typically, columns are colored in order to show similarity or variation. Cells also might be empty if text unit doesn't contain a variant rating for the token. Here we can see two examples, collatex and a comparatio. It's easy to spot aligned patterns on word level. Sentences also can be easily followed since an entire line is reserved for each sentence. It works very well with for less varying text fragments. We have also here a limitation that the screen size limits the number of text variants they can be compared. The last technique is text variant graphs. They employ a graph structure to represent word-level variations for short text fragments. It's tailored to visualize collation results. Variant graphs. A graph is a directed acyclic graph with nodes typically representing words for text being aligned, and each stands for a pair of subsequent tokens. Each text variant contributing to the graph defines a path in the variant graph. Here we can see example, Stemma Web and TransVis. The size of the nodes may reflect how often a word appears among the editions. Edges can be labeled or colored to inform on corresponding variants. As tabular views, a variant graphs currently only work on word level, at best with short, less varying text fragments. In contrast to tabular views, variant graphs reduce redundant information by merging equal or similar tokens. Now we move to the design implications and the future challenges concerning different features of an alignment scenario listed in this table. We classify the visualization techniques according to applicability with the green fields, potential applicability with the orange or yellow fields, and inapplicability here the red fields, which indicate a future challenges. For adopting one of the discussed techniques or innovating a new visualization model for textual alignment, one should consider these 5 factors points. Alignment task, if the underlying task is collation or text reuse or translation alignment, the number of variants, the text hierarchy levels, are we working on sentence or word level or paragraph level? Do we need to use a navigation bar or overview? Language, here we can see all discussed techniques are applicable to monolingual corpus, as we can, not all of them are applicable for multilingual corpuses. Text stability, less varying text give users, of course, more freedom to select an appropriate visualization technique. Drawing from our own experience in developing text alignment visualizations and the open challenges highlighted here in red color and red fields, we derived some future directions. The need for a modular system. Our observations when preparing the survey exposed a high number of redundant tools solving one and the same issue. A modular system applicable to any related text alignment scenario would be an appropriate strategy to prevent this issue. The need for scalable solutions, as we can see here, we have just one technique, scalable solution here, the text heat map. So scalable text alignment visualization techniques represent a significant future challenge. Also, the need for document-based visualizations. Here we have only one technique can implement or can present the relation, the alignment relation at document level. So we need document-based visualizations. Variant graph opportunities, as we can see here, that the current design is not applicable to the entire variety of textual features. For example, what we can do, the structure of variant graph might be valuable to support manual alignment scenarios. It could also be applied to analyze the alignment at sentence level, Also, since variant graphs are defined as directed acyclic, and inclusion of loops to overcome the issue when dealing with unstable text could be a beneficial extension. Exploring new datasets and alignment levels, such as the alignment of OCR output and the alignment at character level, or the alignment of movie subtitles. Technique transfer to related domains, like visualizing the alignment between other data types. For instance, variant graphs could be applied to visualize alignment among protein sequences. Side-by-side view can be employed to alignment among musical scores, or sequence-aligned heat maps can be applied to visual audio signal alignments. Thank you for your attention.
All right, thank you very much, Tariq. There is one question from the chat, which is, did you also consider corpus level alignment in your survey?
Yeah, sure. The fact that there are not so many tools that consider the corpus level alignment, there was only one called the Chinese text project, which use the network graph to show the relation between the document and the corpus. As I mentioned, we need like the document-based visualization, because there are not so many tools offer this kind of visualization.
Mm-hmm. And then I have another question. So is it, given this range of different visualizations, is there any platform or implementation of these visualization techniques to sort of try them out on my own data sets? Or if there isn't, have you planned anything?
Actually, we mentioned that there are so many redundancy in the tools. Most of them implement the same thing, and we need like a kind of modular system where you can use, you can apply the visualization on your own data set. Actually, I and my supervisor, Professor Stefan, were planning to implement such a tool where it's kind of alignment visualizer, where you can just upload your dataset and you can try different kinds of visualization on the same dataset.
That's cool. That's pretty exciting. I'm looking forward to that.
Yeah, thank you.
All right, so thank you very much. And our next speaker is going to be Fumang Yang, and she is going to talk to us about a virtual reality memory palace variant 8's knowledge retrieval from scholarly articles.
Hello, this is Fumang Yang, and I'm a fifth-year PhD student at Brown University. In this video, I'm presenting our work entitled A Virtual Reality Memory Palace Variant is Knowledge Retrieval from Scholarly Articles. I'm most excited about the components of a virtual reality memory palace and knowledge retrieval. The purpose of this work was to explore the value of virtual reality to help people, like researchers, effectively remember scientific knowledge. So, what is a memory palace? A memory palace is a powerful mnemonic device to help people quickly and effectively remember information. It evokes our spatial memory and uses spatialization to aid recall. To build a memory palace, we follow 3 steps. First, we need a list of items that we want to remember. In the literature, this is usually a list of words, like a list of names or a shopping list. And here we are going to use the co-author list of this work as an example. I'm sure that at this point you have forgotten who the co-authors are for this paper. Second, we also want a list of loci to provide spatial information, serving as the palace. This is usually a place or a scene that we are familiar with, like one's home. Here we are going to use my virtual apartment as an example. It is indeed a replication of my apartment in physical reality. Third and the last, we need to build connections between the items and the loci we chose. This procedure requires our imagination to build a mental visualization. So, the second author, Jin, is doing research about augmented reality on smartphones. Let's put him along with this virtual phone. The third author, Johannes, he plays video games. Let's put him on top of this monitor since he might have one too. Next, David Batter is a professor in the Department of Cognitive Linguistic and Psychological Science. Let's put him along with this stack of statistic and experimental design books because he might have one of these books too. The second to last author, Colin Jackson, is considered an external collaborator, so we put him along with this virtual window to imply that he is outside of Brown. Finally, the last author is my advisor, David Laidlaw. Let's give him the best in this room and put him along with the flowers. To reinforce our memory, Jin is doing research about smartphones. Johannes plays video games. David Batter might have one of these books. Colin is an external collaborator outside of Brown, and David Laidlaw is my advisor, having the flowers. We are good with the connections, and now we remove all the pictures. To recall, we imagine that we work through the loci and pick up the connections we just built to help us recollect the co-author list. The intuition behind this is that it is easy for us to remember our home, as I have stuck here for more than 7 months. And this familiarity with spatial information will guide us to the information we want to recall, while the connections we build. Let's try to recall now. First, we see the phone. We know this must be Jin. Then we see the monitor. We know this implies Johannes. Next, we see the stack of books. We know this implies David Batter. And we see the window. We know this implies Colin. Last, we see the flowers. We know that must imply David Laidlaw. Now, we have a memory palace to remember the co-authors. Usually, remembering a list of items like names is not quite useful. People might want to use the memory palace to remember semantic information. Researchers might want to remember scientific knowledge in a stack of papers. Also, when we have a lot of information to remember, we need a much larger spatial space. This requires lots of training and is often quite hard to build a memory palace for. We could use virtual reality to provide a large set of spatial loci, which also eliminate noise and unexpected interruption. All of this motivated our research of using virtual reality to provide rich spatial information to help people remember the scientific knowledge in scholarly articles. We set up a virtual reality coffee shop scene that could be familiar with the potential participants like college students. For experimental design purpose, we select 4 loci for the participants. They are, first, the coffee display, second, the shelf with food, and third, the cashier desk. The last one is a coffee bag basket. We use the abstracts from the journal Animal Cognition to represent scientific knowledge. In this virtual coffee shop, participants can walk around. They read these 4 abstracts in virtual reality and build connections between the abstracts and the loci we picked for them. In particular, they were instructed to not memorize the abstracts word by word. They were asked to remember the main ideas in the abstracts. The task was more difficult than remembering a list of words and required a semantic understanding of the abstracts. Participants had to make sense of the abstracts before they could build the connections. For example, for the abstract about elephant, they might want to imagine an elephant running on top of the chip bags. Note that we did not instruct how they should connect the ideas in the abstract to the loci. It was up to the participants. Since this mnemonic is slightly different from building a conventional memory palace, we call it a virtual reality memory palace variant. To understand the effectiveness of such a virtual reality memory palace variant, we compared it to a condition where participants only used spatial information in a picture on the screen as their loci. We term this an image-based memory palace variant. And also for comparison, we had a baseline condition where all the participants read 4 abstracts on the screen, and we did not give them any specific strategies to follow. In total, we had 3 experimental conditions. We recruited 26 participants from our campus and nearby institutions. This was before COVID-19. They were randomly divided into 2 groups of 13 participants. Each group of participants first finished their baseline condition, and after 3 or 4 days of a forgetting period, they came back and finished the second condition. In any of the 3 reading and remembering sessions, participants had up to 30 minutes. After 30 minutes, they were asked to stop reading, or we removed the reading materials from them. Immediately after reading, participants were asked to recall on a desktop and also recognize a list of 10 sentences. We used both accuracy and precision to measure participants' recall and recognition performance. We graded their recall by counting the number of the ideal units in their answers. We grade their recognition by counting the number of the sentences they recognized. Accuracy is the correct number of ideal units or sentences, while precision is the total number of ideal units or sentences. For data analysis, we use 95% bootstrap confidence intervals and coherency for each condition. We also use the linear mixed effects model to compare the 2 memory palace variant conditions. We had 2 main observations from the results. First, compared it to the baseline condition, both memory palace variant conditions improved participants' recall and recognition performance, especially for the virtual reality condition. The effect size could be large, but we were not able to estimate its actual size given the data. Comparing the 2 memory palace variant conditions, the virtual reality condition is an improvement over the image-based one, but effect size is very small. We also performed post-hoc quantitative analysis on demographic factors and locomotion data. As a result, we did not find any of these factors explaining the difference in participants' performance. Last, we performed a thematic analysis of the anecdotal feedback from the participants. We found that first, 10 out of 13 participants thought the virtual reality coffee shop was reasonable for the task. Second, 5 out of 13 participants reported that using virtual reality could be distracting. The headset was quite heavy, and the scene was stretching sometimes. Last, Some participants reported that they were able to associate an ideal unit in an abstract to a small object in the virtual reality scene, and this may help them build a hierarchical memory palace. This structure may also align with the processes of natural language understanding and spatialization. For a deeper discussion and details like experimental design, training, practice, instructions, as well as data analysis, please refer to our manuscript. To summarize, we hypothesized that a virtual reality memory palace variant could aid knowledge retrieval from scholarly articles, and this is the fundamental difference between this and other studies of a memory palace variant, as most of them focused on remembering a list of items. Our task was much more difficult and might be relevant to semantic memory. We used the virtual coffee shop scene and found that connecting the ideal units in the abstracts to the spatial information in the scene could aid recall. Thank you so much for listening. I'm happy to answer any questions.
Thank you very much, Fumang. This is really fascinating work. There was a range of questions on the chat. A couple of them were about scalability. How scalable is this technique to the number of authors or the number of items to memorize, but also with respect to the information type, especially if because some concepts don't have a clear spatial representation?
Okay, I think at least there are two set of questions here, and the first one is about scalability in terms of the number of items. I would say this is a wonderful question. So first, at least I don't believe that this is going to scale for like thousands or hundreds of abstract at one time. I think one of the previous pair in this session about analyzing the essays, that might be a better approach for this, but we could put such a video analytic system inside virtual reality too. But in terms of like for people, like researchers like us to remember like papers, we are not going to remember hundreds of papers at once, maybe just 10 per day. And we could repeat using, building a memory palace per day for like 10 abstracts or papers for each day. Like I think at least one memory palace might be helpful to remember all the papers in this session. And in terms of the number of authors, because they are just one item, I think I saw literature where like people are able to using a memory palace to like remember at least dozens, maybe 50 different like items and English words. That's my answer to the scalability. In terms of what type of information, I think this technique might be more helpful in terms of helping people remember like concepts and knowledge that has a shape which we can imagine. But I also got such like some feedback from like a colleague in the math department asking me whether this is helpful to like remember like math concepts, because mathematics are supposed to be very abstract. I would say like if like we can visualize these abstract concept in virtual reality, we can still using like our spatial memory to help us like memorize like how one abstract concept related to the other. Yeah, that's my answer to this, like what types of information this technique can help people to remember. Thank you so much.
All right, well, thank you very much, Fumang. There is a number of additional questions. Maybe you can join the chat after the session and answer some more of them. All right. Well, thanks a lot. And our next speaker is Hannah Kim. And she is going to talk about her work, Architects, Interactive Hierarchical Topic Modeling.
Hello everyone, I'm Hannah Kim from Georgia Tech. In this video, I'll talk about our paper, Architects, Interactive Hierarchical Topic Modeling. Topic modeling is one of the most common ways to understand and organize large-scale text data without reading through every single document. Using topic modeling, we could get a topical overview of the data where topics are computed as distributions over keywords, and documents are represented as weighted combinations of topics. The problem is that even the state-of-the-art topic modeling techniques suffer from several limitations. First, they could generate poor quality results, including topics that contain generic words, incoherent topics that do not make sense, or there could be multiple similar topics. Sometimes, a topic's top keywords may not match with its top documents. In addition, even when the topic quality is really good, the computed topics can be different from users' perspectives or their interests. For example, let's say you are running topic modeling on research paper dataset, and you expect the topics to be based on their application areas. But the computed topics may be based on what kind of techniques are used in those papers. Similarly, you may want different levels of granularity than the computed topics. One way to mitigate these limitations is human-in-the-loop topic modeling, so that users can interact with the model and steer the analytic process. In the visualization community, there have been many interactive visualization tools for human-in-the-loop topic modeling. These tools offer great functionalities in exploring topics, topics' top keywords, and their corresponding documents. However, in terms of model steering and model refinement, there have been two major challenges: scalability and limited steerability. Let's talk about scalability first. Most existing systems can handle up to thousands of documents, but they're not well suited for large-scale datasets in practical scenarios. Big dataset usually requires a large number of topics, and computation and visualization of many topics are limited by computation capacity, screen size, and human perception. Additionally, systems with more flexible interactions tend to be less scalable. Therefore, we need an efficient and scalable way to interact with a massive set of documents. To deal with large-scale data, we use hierarchical topic model. Traditional non-hierarchical model treats all topics as the same level without considering their semantic granularity. On the other hand, hierarchical topic model can represent information at multiple levels of detail for better understanding of the data, and it can allow interaction at different aggregation levels, so that user could better organize the documents. And since the users can zoom in on a specific topic and its subtopics, they could focus on steering unclear parts and leave the rest to the computational algorithms for improved efficiency. The second challenge is limited steerability. We surveyed existing topic modeling systems with model steering interactions, and we divided the interactions into three groups based on interaction units: word-level interactions, document-level interactions, and topic-level interactions. To summarize, Many systems support non-hierarchical model refinement interactions, but not all interactions are supported in a single system. And only a few systems support hierarchical topic organization, but they support none or very limited word or document level interactions. One reason is that many systems are built on top of existing automated algorithms, which are used as black boxes. So their interaction capabilities are limited by the algorithm's parameters, which are not easy to understand and even harder to tune. In this paper, we offer flexible steering through tight integration. We advocate that visualization systems, underlying algorithms, and user interactions should be tightly integrated, meaning they should be jointly developed, where all three components are considered from the start and throughout the entire design process. To help with implementing tight integration, we came up with more specific design goals. I'm not going to go over these, but please refer to our paper for more detail. And these are the model steering interactions that we support. Most of the interactions are from the related work, except for a few interactions that we introduced. And each interaction is directly linked to model change and fast algorithm update. As a proof of concept, we built Architects, a visual analytics system that shows multi-level overview, allows topic exploration, and supports various model steering interactions, such as creating, ignoring, refining, and reorganizing topics, and guide users throughout the model steering interactions. Now I'm going to show you a little demo of our system using the TED Talk dataset. TED website has various talk videos, but navigating the web page is not easy. They have very specific topic text like these, but there are no high-level grouping or taxonomy to see overview of the videos. So we gathered transcripts of the videos and used our system to build hierarchical topics. This is our topic workspace. It has topic cards and mini overview. The mini overview shows a vertical cut of the hierarchy. On the other hand, the topic cards show a cross-sectional cut of the topic tree. A topic is visualized as a card where its height is proportional to the topic size, and each topic card has its top 10 keywords along with bars showing the keywords weights. If you flip a topic card, you can see the documents that belong to the topic. You can change the depth level of shown topics with the top buttons. Now we see the first level and the second level topics, which have lighter shades. And non-leaf nodes are minimized to save space. Now I'll demonstrate how to build a topic tree. Let's examine topics. The top blue topic is a bit ambiguous, so I'll split it to make sense of it. As a result, we have a subtopic about learning and another subtopic about gender. Okay, good. I think this music topic is not close enough to learning or gender, so I'll move this topic under the root of the tree. And we have 7 top-level topics, including the music topic that I just moved. Next, I'll split more topics into finer-grained subtopics. And I'm gonna fast forward the demo of doing that. After several split interactions, we have more topics. There are 3 orange subtopics. The first one is about sustainability, and the other 2 are about economy. And the purple top-level topic has subtopics about nature conservation and astronomy. Since sustainability is a big issue nowadays, I want to combine all sustainability-related topics. When I start dragging the orange sustainability topic, you can see that several rectangles are highlighted, including the nature conservation purple topic. This is what we call interaction assistant. Our system recommends where to drop the topic based on similarity. So when you want to merge or move topics around, you don't have to inspect all the other topics. And our interaction assistant works with words and documents as well. You can also delete uninteresting topics by dropping them into the trash bin. And deleted topics can be restored later using the trash bin menu. Finally, I noticed that there is no sports-related topic. In this case, I could create a new topic using sports-related keywords. And this new topic is so small, meaning that there were not many sports talks in our TED dataset. In this demo, I only showed a few interactions in the topic workspace, but there are other views and interactions that Architext offers. So please check out our paper if you're interested. Now, I'll briefly explain underlying algorithms for our interactions. We have 5 interaction primitives, which are the building blocks for constructing our steering interactions. First, for primitives, make children, merge, insert, and cut are 3 operations, and the last primitive, recompute, is a topic refinement operation utilizing a constrained NMF topic model. For example, removing some keywords from a topic is a combination of making 2 child topics, recomputing the child topics so that one topic is about the selected keywords, and finally cutting the topic out from its parent and ancestor topics.
Yes.
To see the full list of our implementation, please refer to our paper. Due to this modular implementation, we can optimize the system performance by fine-tuning the 5 base primitives, and it's easy to add new interaction by combining the primitives. In conclusion, we propose Architext, an interactive hierarchical topic modeling system that can handle large-scale datasets and offers flexible steerability. If you have any questions, feel free to reach out, and thank you for watching.
Thank you very much, Hannah, for this talk. There is one question from the chat was, how would the system work for dynamically changing collections? Does it work for collections, or yeah, do you have any insights on that?
So this is what we actually have thought about before, but currently our system does not support any dynamically changing collections. So right now, we don't use any external information like timestamp for authors or something like that. We only use raw text of the data set and just create topics. So if we want to create topics for like newer data set, we have to do this again. But as a future work, we're working on a new system that are dealing with dynamic topic modeling that could deal with streaming text data. So stay tuned.
All right, okay. What do you see as the typical use cases of the systems do you anticipate that users would make severe or drastic changes to the original model that matches their mental model, or is it more about is the typical use case more fine-tuning the model?
So I think this is a good question. I think that depends on the quality of the data set and among other things. So if the data set is really well structured and have very clear taxonomy, then I think fine tuning is enough. But if your data set is kind of dirty or not cleaned well, like social media tags, where you have like multiple different choice of words and stuff, then you'd have to like drastically interact with the underlying model to get a finer and clearer model that will match your mental model.
All right, great. Thank you very much. There were a couple of additional questions. Maybe you can join the chat after the session and answer them in chat there. All right, so thank you very much. Our next speaker is Yousef de Rose, and he is going to talk about his system attention flows, which can help us analyze and compare attention mechanisms in language models.
Hello everyone, my name is Yousef de Rose, and today I'll be presenting with Jia Wang on attention flows, a visual tool for analyzing and comparing attention mechanisms in language models. This research was done in affiliation with Vanderbilt University and was done in tandem with Matthew Berger. First, I present a simple natural language processing task of textual entailment, where the objective is to predict whether a second sentence entails or can be inferred from a first. Here we have the Bermuda Triangle lies in the Atlantic Ocean off the coast of Florida, and we can see that this is clearly entailed by the Bermuda Triangle is near Florida. We can identify this by picking out some key words. When we do this in a machine learning sense, we pass both of these sentences into a model, and it predicts with relatively high accuracy that it is entailment. However, with deep learning, it's hard to understand what models are learning, and we want to see, do these models actually pick up on the relevant information for solving these tasks? The models in question are trained in two ways. They are pre-trained and fine-tuned. Fine-tuning is your more standard sense of training for a downstream task, where pre-training is to generate a holistic understanding of context through a trivial, unsupervised set of learning objectives. And the reason for pre-training is that it simplifies a need for heavily engineered task-specific architectures. The model that we study is pre-trained in two ways. First, it uses mass token prediction. Mass token prediction takes a sentence and randomly masks some subset of words from that sentence. We then ask the model to predict which words in the vocabulary were masked. The second objective, next sentence prediction, takes a first sentence from somewhere in the corpus and a second sentence that either follows or is random. And then we have the model predict whether or not these sentences are in fact following one another. This sets the objectives of our research, and our objectives are first to understand how self-attention forms classification, and we would like to understand how the model in question makes decisions via the words that it attends to. And our second objective is to understand the refinement of self-attention during fine-tuning. We would like to assess what was learned by the model when it's fine-tuned for a specific task in order to confirm that the model is learning relevant information. And our contributions to this are attention flows, a visual tool for understanding how deep attention-based language models make predictions for NLP understanding tasks and how their attention is refined during fine-tuning. To further explain our tool, we'll now discuss self-attention and fine-tuning details for the state-of-the-art transformer model. The transformer model is typically constructed of encoders, and an encoder takes an input sentence and extracts relevant information encoding it. People who are familiar with transformer models may typically see it with an attached decoder for translating the encoding. However, we are only going to focus on the encoder today, as that's what our model uses. Transformers are built by stacking encoders, and the input is passed through each of these encoder layers sequentially. The model in question, the bidirectional encoder representations from Transformers model, or BERT model, uses 12 layers. Inside of each layer, the input is passed through a self-attention mechanism and then a feed-forward neural network. The self-attention is what makes transformer models so robust and is the focus of our research and a number of other tangential research objectives. Self-attention essentially helps the different layers of the model focus on relevant parts of the input sentence to generate context. And it shows how, for given a specific word, the influence of different words on the next layer embedding of that word. Given an example, the animal didn't cross the street because it was too tired, we know that it may refer to a variety of things. So by looking at the attention, we can see that the tokens the and animal attend highly to it, thus showing that the model is in fact capturing the context. It also shows that at the next layer, the embedding of it will be highly influenced by the embedding of both the words the and animal. This is for a single attention head. However, in practice, often we use multi-headed attention. In this, we pass the input through multiple attention heads in parallel to capture a broader range of relationships between words. BERT has 12 layers and 12 heads, so we generate a total of 144 separate self-attention mechanisms, producing a wide array of attention patterns as shown below. These wide array of patterns mean that heads and layers must encode different information or have different functionality, and this is the key reason for our research. When we fine-tune the BERT model, we take the input and we pass it through the model and generate an embedding at the last layer. We prepend a reserved classification token and use the embedding of this classification token to determine our predictions. Some related work such as XBERT and BERTViz have tried to design visualization tools that create a more general understanding of attention in transformer models. Our design is unique in that it specifically focuses on fine-tuning so that we can probe attention with a specific goal in mind. The key piece of attention flows is something known as the attention graph that we generate. As mentioned, when fine-tuning a model, we start with the classification token at the last layer, as this is what is passed for prediction. First, we identify tokens which have a high threshold, which are above a threshold of attention, meaning that they have high attention values and highly influence the classification token's embedding. We do this across all heads at the last layer. We then take these words and use them as a key to query the previous layer for new attention values above the threshold, and we again pick out these values. Doing this, we generate a directed graph starting at the deepest layer of the model and the classification token and going towards shallower layers. And this graph highlights which tokens were most influential sequentially in influencing the classification embedding and ultimately the end prediction of the model.
So here is our visualization approach. For the model's attention heads, we encode them in two manners. The first way is that, adjacent to each token, we encode its attention heads as a set of 12 small glyphs, where the color encodes the number of tokens the head attends to in the previous layer. This design allows the user to examine token dependencies, such as determining if a set of heads collectively attends to a large number of tokens. We also visually encode tokens that are being attended to in the input by mapping the relative positions of tokens at the next layer to spark lines under each dependent token at the current layer. The height of the peak encodes the number of attentive heads involved in the dependencies. This allows the user to quickly assess whether self-attention is localized or more globally distributed. For our main view, we deploy a radial layout, where each ring of tokens corresponds to a given layer. Starting from the classification token at the last layer, each preceding ring contains tokens from the prior layer that have some influence on the embedding of the tokens in the next layer. This allows us to trace token influence throughout the model. To provide context with respect to the original sentence, we depict the position of tokens found in each layer in an auxiliary radial view here in the upper left corner. Here, each token's position in the original sentence is encoded by angle. To increase readability, we show the first sentence going clockwise and the second sentence going counterclockwise, meeting at the thick line here. We allow the user to view subgraphs by hovering or clicking on a token. For a selected token, we highlight tokens at subsequent layers that depends on it, as well as all tokens at prior layer it depends on. A pair of tokens are considered dependent if there exists a path between them in the attention graph. The user may also hover or click on a head glyph for a given token to limit connectivity to that specific head. To select token sequences, we support brushing within the layers, where we highlight the intersection of the attention graphs for the brush tokens. This can be used to assess whether contiguous text bands have similar attention patterns. We also support token selection across the layers, highlighting the set of heads through which the attention flows. Moreover, for tokens that are not in adjacent layers, we highlight intermediate tokens and their attention head on the path between the selected tokens. If multiple tokens are selected in either layer, we show the intersection of the attended tokens. Our design also supports model comparison. All the interactions we support for single model, such as token and head selection and brushing, are supported in the model comparison mode as well. We take the union of tokens attended to by each model and visually encode them with model-specific colors. Turquoise stands for the bird model, while purple stands for the fine-tuned model. If a head has significant attention in both models, we split the head glyph in half to show shared attention. If a token is attended to by both models, we color the token in orange. Now we showcase our visualization through some use cases. We evaluate our tool on 3 of the 9 sentence pair binary classification tasks: the RTE, Mrpc, and QNLI. RTE asks the model to determine if the second sentence is an entailment of the first one. In this example, the first sentence entails the hypotheses found in the second sentence, since will receive the proceeds imply proceeds go to regarding the family. The user can select the token go at the later layer and receive at an earlier layer to understand the model's attention flows between these tokens. We can see that starting from the token receive, the fine-tuned model attention crosses to the second sentence, gathering necessary information for classification before it finally arrives at the token go. The QNLI task asks the model to determine if the second sentence contains the correct answer to the question in the first sentence. In this example, the classification is positive. We can see that when we select the token word, what year, we find that the answer part, early 1950s, in the next layer is highlighted, indicating that there is a dependency between these tokens inside the attention flow. However, we can see that the pre-trained model fails to attend to the answer across multiple layers. The Mrpc task asks the model to determine if 2 sentences have the same meaning. In this example, the second sentence is not a paraphrase of the first one, as the person said different things. In this case, when the user selects the token said, we can see that only the fine-tuned model attends to what the person said in both sentences. In conclusion, we introduce attention flows, a visualization that helps in exploring self-attention mechanisms during model fine-tuning process and how that informs the model with classification decisions. As for future work, we plan to incorporate other aspects, such as contextualized embeddings, into the tool to generate a more comprehensive view. We also plan to extend our approach to support more general model comparison. And lastly, we would like to support querying multiple samples that have similar patterns and let users to compare across different samples. We hope this can help investigating further into the models and datasets. And here we provide an observable notebook link of our implementation. It includes several samples of the 3 tasks. So feel free to use this tool and see if there is something interesting you find. Thank you very much.
Right, thank you both very much for this talk. I have 2 questions about the approach. So this is specifically designed to compare and analyze models. Have you thought about extending this approach to let users actually make changes to models based on their?
We actually built the design very fluidly. So the idea would be as long, like the data is prepared on the input side, there's actually no dependence on the model once you're in the design. So you can actually use any style of transformer or self-attention based model as long as the input is generated using specified scripts that we built. Like you should be able to transform your input your model, like your input from your model into a visualization format that would be suitable with our visualization.
And then another question from the chat is, who are the intended users of the system? Did you work with domain experts on this? And well, who did you have in mind when designing the
Sure. So we, as we were building the tool, like our lab is very focused on natural language processing, but we consulted a lot of experts towards the end of our visualization design. The desired users of this tool would be people who are trying to debug fine-tuning tasks or specifically data sets we see for users using this model. It provides a good way to look at maybe outlier sentences or maybe specific examples that are maybe bogging down some training process. And we also see that some future work that could be implemented could also be used to influence model design, but we would require some extra development on how the actual embeddings are encoded in the visualization.
And then another question is, what are the reasons for using a circular layout for this main view of the design rather than, for example, a linear layout like a rectangular heat map?
Sure. We actually tried a linear layout at first, and one of the things that we noticed is that a linear layout actually wasn't very conducive to discovering patterns when using a user interface. One of the things that led us to the radial layout is that when you investigate the tokens, like the token sets at each layer that are highly attended to, you find that these increase by actually a linear factor as you go up and as you go to shallower layers in the model, and that factor actually very much correlates with a radial layout in the number of tokens that would be added by increasing the radius. And those two factors together were the main things that led us to using a radial layout instead of a linear one.
All right, great. Yeah, thank you very much. And with that, we are at the end of our session. Thank you very much, everyone, for attending. And I wish you all a good rest of this virtual conference week. Thanks a lot. Bye, everyone.
How to know if a graph is correctly drawn? Are all the aesthetic properties preserved? To answer these questions, we currently use quantitative methods that require graph structure and are computationally expensive. We propose a new method to directly compute these metrics from graph layout images using convolutional neural networks. Below are the results. To know more about our approach, please attend our talk.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We used data from today's United States to recreate 7 abolitionist data visualizations, which were originally presented by W.E.B. Du Bois in 1900. Comparing the modern and historical versions, we can see continued racial disparity in America's geography, economy, education, and justice systems. This view of the past alongside the present invites us to look at the historical context for modern-day abolitionist movements.
A short overview of the presentation for a simple pipeline for coherent grid maps. In a grid map, we transform an input map to a tile arrangement. However, current approaches do not perform well on complex maps such as the Netherlands. We propose a pipeline that generates high quality and coherent grid maps even for complex data using a simple pipeline.
We present an exploration into co-located collaborative immersive analytics in a prototype called Fiesta, the free-roaming immersive environment to support team-based analysis. The prototype allows groups of users to visualize and explore their data in a room-scale environment, which we used in an exploratory study involving 10 groups of 3 participants. We focus on the roles which 2D surfaces have, as well as how users leverage the 3D space during both the individual and collaborative work.
The make of continuous color maps. We present the CCC tool, a new web tool for the creation, editing and analyzing of application-specific color maps. For the precise definition of color maps, we developed a new color map specification. This new structure increases the editability by reducing the numbers of colors to a minimum.
Hi, please come see our talk if you are curious about how to encode your data so that it can be efficiently queried later at different fidelity levels by fetching only the relevant bits from the disk. The talk is titled Efficient and Flexible Hierarchical Data Layouts for a Unified Encoding of Scalar Field Precision and Resolution.
As visualizations begin to use color, shape, line, and form in new ways, legends often go overlooked as essential to interpretation. To address this issue, we created a web-based interface that renders and formats legend entries, presenting the dynamic properties of glyphs, lines, and surfaces, and increasing nuanced object recognition in artist-driven 3D scientific visualizations. Each legend entry includes the variable name, full value range, and artist-chosen artifact.
This paper explores the efficacy of using narratives as a medium of explaining the causality in causal networks. Now, towards this end, we provide you a glimpse of CausWorks, a causality visualization system for generating narratives given a set of interventions and objectives for a causal model. And we further validate CausWorks through interviews with experts. Please read our paper to know more. Thank you.
To uncover football tactics, we create spaces and times. We use time query, construct spaces, construct times. Our approach was used for reconstructing team tactics in different classes of game situation. Our domain experts are happy, and the Germans shall win again and again.
This study proposes a taxonomy of sentiment data visualization based on visual metaphors. In order to create a taxonomy, we enhanced a group of classification criteria. And then, we classified a total of 35 papers published in the last 20 years. As a result, we presented the guidelines for researchers doing research on the sentiment visualization and visual metaphors.
Our paper describes the motivation, ideation, and prototyping of a novel visualization tool to support voice training for transgender people. We centered our design around user needs and lived experiences in order to support self-determination of gender expression. In so doing, we make novel inroads in how to visualize speech data and open possibilities for future work in the design of visualizations that prioritize user agency.
Dimensionality reduction is an important tool for the visual exploration of complex high-dimensional data. Most existing techniques focus on preserving the intrinsic geometry of the data during the projection. However, important information can be encoded within the global structure of the data. To address this, we present TopoMap, a dimensionality reduction method that provably preserves the topological features of the data during the projection.
How do people really make use of space to spatially organize their ideas? To answer that, we collected 280 images from the web, which came up by searching keywords such as brainstorming. And we found spatial organization patterns and interesting observations about how people make use of space.
you.